Good morning. Good morning to all. Am I audible? Hope I am audible now. Am I audible, please? Okay. We'll start within 2-3 minutes. Good morning to all. So today we will be learning about the if you remember the vector control control schematics or the simulation. In the direct axis there will be a PI regulator, and in the quadrature axis there is the outer loop and there will be an inner loop. So there are several techniques to tune those three PI regulators. I'll be explaining the most common technique which is used by the people who are working in the field. Then first I will discuss it, then I will simulate it. I'll be showing the technique through MATLAB or Simulink. Then I will show you one medium voltage drive, graphical user interface. So during that last year, I think there is that one disaster was there, Amphan. During that time, some of the pump house got some problem in the motor. So this is a high power motor, maybe around 5 megawatt tunnel. So that motor I tuned, another motor replaced with different parameters or these things. So I have tuned from here the drive using TeamViewer, so that what is the interface of that software I will show you, so that you can correlate whatever we have learned, why we learned all these things, where it will be utilized. All these things I will be explaining, and if afterwards time permits, just I will show you the, because already you have learned how to generate PWM. Just I will modify slightly that code and I will show you how to generate sine PWM. So this is the agenda of today. So hope I can, now I can start, I think. Okay, so today we will be learning about the direct and quadrature axis tuning of the vector control. So if you remember, so this is my in direct axis, this is my reference flux. That is going to one comparator. Flux is produced through the stator direct axis current. So this feedback I am taking from stator direct axis current, which is coming from ABC to DQ transformation. Then there is a PI regulator. . and this is generating the stator direct axis voltage. For the quadrature loop, so this is my reference RPM, which is compared with the speed feedback coming from the motor, that through encoder. Then there is a PI regulator. This is generating the torque reference. You know, torque is, already we know the torque producing component is nothing but the armature current component, which is nothing but quadrature axis component. Sorry. Then this is again going to one comparator. This is coming from quadrature axis current of the machine, which is again coming after that ABC to DQ transformation. Then it is going to one PI regulator, and then it is generating the quadrature axis voltage reference. Even everywhere there is some limiter. There is some limiter. Limiter is there everywhere. So this 3 PI, this is direct axis compensator. This is the quadrature axis outer compensator. This is the quadrature axis inner compensator. So this is for torque flux regulation. This is for torque regulation, and this is for speed regulation. So we will be knowing how to set this Kp and Ki. Okay. So already we know something about the induction motor, and we understood that all these things, flux, RPM, torque, everything, they are coupled together. So in the last class we have seen that to tune properly, to obtain the best dynamic performance of a plant, if you include any compensator, so the first duty is to identify the open loop system transfer function. Then you have to, the transfer function will be multiplied by the transfer function of the compensator, which will definitely increase the order of the system. Again, you know, for the higher order system, there will be there is a possibility of nonlinearity in higher order system. You should be very careful during the selection of the regulator. All these things, all other things should be considered marginally. It is to be optimized. A requirement should be first you have to find out your requirement which is optimized. Marginally you have selected. It should not be high, should not be low. Then it will be very difficult for the control engineer to achieve the goal. Okay, so we will be tuning these 3 PI regulators. As I was telling, getting the decoupled transfer function, it is difficult, but still we have to consider some fair approximation so that we can reduce the order of the transfer function, and also we have to consider that the information during transient should not be eliminated by those approximation. So as this course is very basic course, so I am not going in depth of the mathematics. I'll be just showing the technique. So you see, this is the first order reduced order transfer function of the torque loop. Torque loop means, this is torque loop means which one? Inner quadrature axis loop. So this is the torque reference which is coming from the outer speed loop, This is coming from the motor after converting to after doing the ABCD DQ transformation, and this is your one PI. This is giving the quadrature axis voltage reference. So this transfer function can be reduced to this form, which is 1 by Rs by S. S is the Laplace operator, and Ts is the time constant of the stator. So Ts is equal to what? Ts is equal to LSS, which is mutual plus self, by Rs. Okay. So some of the places the PI regulator is represented by, somebody will be represented by Kp plus Ki by Ks. Somebody will be representing K into 1 plus St by St. So if you split this, so it will come K plus K by T by S. So if you compare these two equations, so this K is the gain and T is the time constant of the PI regulator. So if this two equation is compared, so my K is equal to basically Kp and my T is equal to Kp by Ki. Correct? This is a representation of PI regulator. So for the flux loop, the transfer function can be reduced to this. S is the Laplace operator, Tr is the rotor time constant. So that is LRR by RR. Already we have. Another thing you have to remember, you can do it. Today I will be showing you to do this tuning using MATLAB. But you can do it these things by your own, by simple calculation also. Okay. In that case, you have to remember few things. So if this is my natural frequency, this is the thumb rule. You remember, my professor taught me, I am teaching you. And frankly speaking, by considering this, I have most of the 99.99% system I am tuning perfectly. There will be some complicated system, unstable system, there only it is problem. So loop. So this is the flux loop. Sorry, first I will put the RPM loop, then I will put the flux loop, and then I will put the torque loop. The RPM loop, as I was telling, the RPM loop is the RPM, the speed loop is the most sluggish loop. It will be most sluggish. So the natural frequency of speed loop is 1 Hertz, and the flux loop is 10 times faster of that. It will be 10 Hertz. Torque loop is the most fastest loop in motor control, which is of 100 Hertz. Okay. Now you see, you know the reduced first order transfer function, the first order transfer function of the each loop, and you multiply the transfer function of the compensator, which is also first order. So these things it will be second order. Okay. So now your closed loop transfer function will be, you can estimate it, your closed loop transfer function. So that is 1 plus GS. Okay, 1 plus GS. So this will be, say for this case, this is this one, and this HR should be K into 1 plus KTS, sorry, 1 plus ST divided by ST. So finally, if you multiply, this term will be second order, and if you do the addition and plus 1, if you do, then these things, finally the transfer function, it will be reduced as omega n square by s square plus 2 xi omega ns plus omega n square. And after doing this, this will be a function of tower K and T. Okay, and it will be these things, it will be in this form. So we know this is the flux loop, so we have to put that natural frequency as 10 Hertz. So omega n is equal to 2 pi f, that means 20 pi. So you can replace this omega n by 20 pi. And as I was telling, for very stable system, you have to take the damping as critically damping. You can consider it is at 1. No transient, there is the possibility of over and undershoot will be not there. Very smoothly it will settle down to its reference value. So if you put that, and the both things if you compare, you will be able to find out this K and T very easily, and that value, that is the value after tuning. Okay, the speed loop, the first order transfer function of the speed loop is this one, where the time constant is the inertia divided by the viscous coefficient of the loop, and the instantaneous torque equation of the motor is given by like this. So from there only it is established. That's the first order differential equation, and here one KT is used, that is the value of KT, 3 by 2 into P by 2 into Lm square by Ls into ISD. Already this we know it is fixed. We will be operating for, this is for constant flux, so we know what is that. So KT will be obtained, and this Tm also it will be obtained, and again the same way. And this loop natural frequency is 1 Hertz. Okay, so this is this much radian per second. So by, and my zeta is equal to 1. So by substituting all these things, you can find out the K and T. Okay, I'll be showing you, don't worry, but by through MATLAB, not by calculation. So these are all about the 3 reduced first order transfer function of this 3 loop. Now I will like to request you to see one video in my channel, which is called, you can search, you can open in YouTube and you can put this high performance dynamic modeling of ASCIM, and you type this exact word, then one video will, one playlist will come like this. So there will be 3 or 4 videos, you can see it, then you can conceptualize whatever DQ reference frame we are getting and actual that whatever, because time is not there, so that's why I'm not covering this, because it will take some time. So in your free time you can see. Another thing I'll like to request you, that you can see one same in YouTube, you can type the word implementation of digital controller in Atmega 328p. Shitanshu, like that you can. Okay, and then it will be one video will come, this video you can see this PI regulator, how it is implemented in microcontroller. You can get a, you can have one idea. Okay, again these things during that next course, this basics of microcontroller, I will be it will be conducted shortly. That time I will be explaining all these things in details. Okay, so now if you see one loop, I will show you unnecessary, but you can practice by your own. You see, I will be tuning this loop. So if you go to help, you see this controller, this regulator is, the transfer function is k into 1 plus st by st, as I was telling. So if you reduce these things to as a parallel connection, so your capital K is equal to kp and your t is equal to kp by ki. Okay, as already I have shown you. So if you remember, so this is my motor transfer function, sorry, motor parameters. It's my motor parameters. So now you see, I have used one simple Simulink block, and here I have given one step function, and this is my PI controller, and this transfer function. Let us see why I retain all these things. You see, if you remember, the torque loop transfer function was 1 by Rs by STS plus 1. So you see, this is the rotor resistance. So that's why I have given 1 by Rs here. In the denominator, this is S tau S. So tau S is L by R. So L means self plus mutual. So here you see the self is 0.00139 and the mutual is 0.041 divided by RS. So that is this one and 1. After putting this, I am going to tune it. So these things, all these things to be considered here. So you see here I am giving 0.48, means the reference it will cross after 0.48 seconds. So you can reduce it as per your own. So I am thinking on my assessment, so this value is, so P is, means the, here you see bottom, your Kp is 0.005 and my I is 1 point, this one. This is a good tuned response in my opinion. So now if I open, you see why it is minus, as I was telling these things, here quadrature current is minus, so I have used here one minus sign, so that's why I put. So the same Kp I am putting, point minus 0.00 this one, and my time constant is kp by ki. So whatever we obtained from the you see this is my 0.005, so I am putting my kp as gain as 0.005, and my time constant is kp by ki, so this is 0.005 by 1.429. If you put that, my tuning is finished. So similar way you can tune all other two compensator, and if you tune like this way, and if you run the machine, your tuning is done perfectly. It will work perfectly. When you will be after this course, definitely you will be applying for some industry, for job and all these things. And if you can, frankly speaking, if you can truly learn that something from the course, and you can represent yourself with all these things in front of any people, any company who are working in this field, definitely you will be selected. This is my opinion, but I don't know how many of you are really understand these things, but I tried my level best to tell you in very simplest way so that you can understand. Here, this is the RPM after tuning. This is the current. You see, very nicely it is tuned. So this is the simulation part. Yes. Now I am closing all this MATLAB everything, because I am going to open one more software. I'll answer the question after some time. Okay, let me finish the things whatever I thought. You see, this is the, as I was telling, frankly speaking, I am not promoting any product or any particular brand in this course. Just I am to make you see, this drive is Altivar 1200, means this drive can be used till 12 megawatt. So this drive I have used for, I think, around 5 megawatt on machine, as I was telling. So I'll be showing you whatever we learned so far, where we will apply. So for that only I am showing you this. So this is the main panel. Here, once you give the start command, here all these things, parameter, electrical parameter, it will be showing, but I cannot give the start command. It will not work because this is not connected with any drive. Only I have the these things, and it is giving some by default something. It's not correct. So here you can see all the internal waveform, because in drive, when it will be operating, that quadrature current, axis current, direct axis current, all these things you can't see. So using this you can see that. Now coming to the parameterization. So parameterization means it is protected, and operator should not do. That is only done by the manager. There is a level of access. Okay. Now it is coming. So these are the all settings. With the general settings, here you can see the how many cascaded level, controller, all these things you can select. I'm not going to, so many things are there, just I'm trying to give you a glimpse. You go to directly motor control, go to motor parameter. So here you have to apply the rated voltage. You can change, that is, that motor was 6600 volt, sorry. So like that you can change, you see, rated voltage, rated current, all these things you can change here. This is the motor parameter. Okay, now you go to the advanced setting, and we learned already the things called vector control. So you see here is that flux reference, maximum torque limit, maximum power limit, all these things you can get from your motor details. Then you see this is the speed loop kp, speed loop ki. The way I have shown you, you have to find out the values, and you have to replace here. This is the torque loop kp and ki, but here in this drive the flux loop, as it is an internal loop, so that's why it is estimated automatically. Drive will, based on all your parameter, drive will calculate the kp and ki. You don't have the access, that is there. Somebody will give, some company will provide, that also you can set, but here you cannot set it. After all these things, if you start the machine, it will operate. This I have given just one glimpse so that you can conceptualize why you have learned all these things, because this is required in practical field when you will be going to work. Now I will be telling you one, because time is there. Already some lecture I tried for the, so first what I will do, I will open the data sheet. Where is that? This one. Very quickly I will show you. You see, already we have learned in some class, some lecture, how to calculate the, how to produce the PWM, how to set the timer for PWM. So here this is a value of this, I have written this as a sine theta. It's a sine theta basically. So for sine theta, what, to reduce the capacity of the memory, what you can do, you can write your own function. That is your skill, that you can do when you will be working with the controller. You see, there is a very nice symmetry for sine. So basically this is your sine wave. So for this you need not to write the entire 360 degree, you just write up to 90 degree. So this is 0, 90, 180, this is 270 and 360. So if I only write, if I only get the value in between this 0 to 90, then for, if it is, say this array is a length of 1 to 100, sorry, 0 to 99 or whatever may be. So that is the syntax. So from 90 to 180 it will be 100 to 1, and from 180 to 270 it will be 1 to 100, but it is of negative side. For 270 to 360 it will be 100 to 1 of negative. So if you in this way, if you can write the code, then you can reduce the flash memory of the controller, so that when you will be working with that, you will understand. And here same I kept 10 bit settings. Timer at the PWM is for 10 bit, and output compare register I have given that 500, and you see here I have reduced for 20 counts, that is the date time. What is per count, all these things you can when you will be reading the data sheet in details, you will be it is very clearly it will be understand. So now I will export that code to generate the hex file. Now I don't know whether it will open or not. Better to close MATLAB. Okay, let it open. Now any question is there, you can ask. Now it is opening. Any question is there, you can ask. Any question is there? It is. I don't know. So many things are opened. No, sir. Your chat box is. Yeah, yeah. Actually, I am not chatting. In this chat box, I can see if I want to reverse the motor direction of rotation, how I achieve that. Is it by changing its, yeah, actually if you like SPWM, SBPWM is also used for motor control. Which one is better for industrial use and electric vehicle? So that is, I'll first answer that phase sequence. That phase sequence means there are two aspects. If it is design aspects, that means the output compare register, that value only you have to change. That sequence change means it will rotate opposite direction. Just use, take one a digital input, and if it is high, then that will be that output compare register, it will be change. If it is that means that sine theta value will change. Okay, that phase, that means that phase angle will change. That value only will put. Say I am using timer 1 is for R phase, timer 2 for Y phase, timer 3 for B phase, and there is some array. There will be some array. That array only you, if a particular digital pin is high, then that any two array you alter, it will rotate reverse and forward. This is the design point of view. For operating, when you are operating, it is no need drive one digital, same way in drive also one digital input is there. If you make it high, if you remember yesterday class, forward and reverse, I am in the drive, I am using one contact. If the 24 volt is going to that Li1, it will start to rotate forward for 2 wire control. And if it is connected to another Li2, it will be started to rotate reverse. Now the second thing, like signed SBPWM also used for the motor control. Yeah, it is used, but it will not matter. It is the just only thing, only one plus point is there, because today the DC side and today the semiconductor side also, it is means both AC and DC side, in the inside the drive I am telling, there is so many devices are available in the market. So that is not a matter. Only thing, only the disadvantage is if you use the sine PWM, the utility is 50%, and for a space vector that will be 57%. So that is the thing, only 7% DC voltage utilization, around 7% DC voltage utilization will be there, but that will not matter. Whatever that is based on your design requirement. Which motor is selected for EV to give an high efficiency and operating torque will be good? Again, this is a somebody is asking attendance link. So in my opinion, today people should move to induction machine uh, for its cost effectiveness, for maintenance, these things. Even though we have to introduce the drives and all, but in my opinion, induction motor will be, should, people should think about induction motor to use in electric vehicle for the future, by considering its cost effectiveness as well as efficiency. Everything you can consider, is in my opinion. I am not operating, again I am telling you, I am from different place. I can I am not texting you. I cannot text you. I am telling you that chat box is controlled by that Pantech e-learning is there, na? There I am not doing. Attendance it will be given. But Is the attendant links are the same for all the? This I don't know. Which type of electric braking used in electric vehicle? Yeah. So normally, broadly, the braking is used the mechanical braking. But as I was telling, the first it is the convention. The first electrical braking will be applied to, if there is a regenerative braking and all these things are there. First that will be applied, and once it is slowing down, then the mechanical brake will be applied for mechanical brake will be applied for completely stop. See, that's why I'm telling I cannot text from here. Please try to understand. I don't know. I am not familiar with all this kind of things. My WhatsApp number is 9445072 948. I am telling once again, my WhatsApp number is 9445072 948. Normally, so far, most of the people they are using BLDC machine, okay, and nowadays some company I have seen in Calcutta, they started some trial electric buses uh, that is of induction motor, even though it is in trial mode, okay. Any other question? And definitely I will be discussing for some 2-3 lectures are still there, so I will be discussing about the BLDC drive. Difference between squirrel cage and slip ring induction motor. Yeah, slip ring induction motor means, normally in case of if you consider the first class, the instantaneous torque equation, if you see that, from that equation it is very clear that the torque is dependent on the rotor resistance. Similarly, if you increase the rotor resistance, you cannot increase that rotor resistance infinitely, because the loss will be added. Okay, I square R loss will be added. So where the high starting torques are required, so as there is a slip ring, you can add some additional resistance during starting to produce the high torque, and once it is accelerated, you can reduce it. So these are the main advantage of slip ring machine. You can increase the starting torque, but the problem is again that slip ring, that it's something will be sliding. So for high power machine it is not advisable, and during the hazardous area you cannot use that. This is the thing only. Other thing, the governing equations and everything, everything will be same as induction machine. And in BLDC machine, what is happening, just we are once the rotor position we able to predict, okay, then at that position only we will apply the voltage, so that perfectly it will be aligned. That stator rotating flux will be perfectly aligned with the rotor. You will get the better performance. That is the thing. Next, any other question? and this is for some subsequent course I am planning with Pantech, that because these are the, I cannot give you the actual picture, just I'm trying to show the thing, but actually you are not able to see. So that all these things I am planning, once this pandemic is over, from the Pantech office itself, their office itself, live telecast will be there with actual hardware, so that you can, again you can I will request, when that course will be conducted, all these people who are joined in this course, they should attend that, so you can easily correlate that what you learned. So any other question, or I will terminate the session? Any other question please, or I will terminate the session? Okay, I think there will be no question. So thank you so much. Thanks a lot.